Now that we have the general theory of what happens to a scalar function or a scalar field when we apply a coordinate transformation, let us now look at the special case of rotations in quantum mechanics. And of course, as you may have already guessed, the scalar function that we are going to look at, in particular in this context, is a wave function describing a standard quantum system. So, let us start by considering a familiar transformation, a rotation through an angle theta about the z-axis. Now, we all know what happens under that. Coordinates change by a transformation which I am denoting by r sub z of theta. X, y, z under this transformation goes to new coordinates x prime, y prime, z prime, and you are all familiar from maybe your +2 days that this is given by x cosine theta plus y sine theta, that's the value of x prime, minus x sine theta plus y cos theta, that's the value of y prime, and z of course does not change, so z prime stays z. We can of course also denote this by a matrix relation, that is the column vector x, y, z becomes a new column vector x prime, y prime, z prime, which results from the action on x, y, z of a matrix. And this is what the matrix we often denote by as rz theta. This is the matrix with elements cosine theta, sine theta 0, which is why x prime is cos theta times x plus sine theta times y plus 0 times z. The other rows are minus sine theta, cos theta 0 and 0, 0, 1. Of course, the last final 0, 0, 1 simply says that z prime is the same as z. The question of course now is, how will the wave function describing a quantum system change under this particular transformation of coordinates? Well, we can have various kinds of descriptions of a quantum system, but the simplest description that we have is that by a single wave function, a single function of the coordinates x, y and z. And for that, the standard rules of the transformation that we had figured out for functions work. So psi tilde, the new wave function for this rotated coordinates at the point x, y, z, is the original wave function psi acting upon a new set of coordinates, or rather the old set of coordinates, the coordinates from which you got x, y, z after applying rz theta. So the coordinates themselves are rz inverse theta x, y, z. And by the way, the inverse of a rotation is very simple. In this case, all you have to do is change the sign of theta, which means cos theta of course stays the same, whereas sine theta changes sign. So it's nothing but psi at x cos theta minus y sine theta, x sine theta plus y cos theta. Note the change in sign of the sine theta in the two cases, and z. So we can define this change, or we can describe this change of the wave function from one wave function psi to a new wave function psi tilde by an operator uz theta. This operator of course is the same as the thing that we have been calling the transformation t earlier. So in the specific case of rotation about an angle, the z axis through an angle theta, I denote the operator by uz theta. So uz theta acting on psi gives me the function psi tilde, and this thing act at x, y, z is nothing but psi of x cos theta minus y sin theta, x sin theta plus y cos theta, and z. Of special interest is the case when the angle of rotation is infinitesimal, for reasons that will be clear very soon. So if the angle theta is now an infinitesimal quantity, let's say epsilon, uz epsilon psi at x, y, z will be the value of psi at these coordinates. Notice that when epsilon is tiny, then cos epsilon is actually 1 to order epsilon. The deviation between cos epsilon and 1 only occurs at the quadratic level, at epsilon square level. So if we are only keeping corrections to order epsilon, cos theta or cos epsilon just becomes 1, Sine epsilon of course becomes epsilon, and hence x cos theta minus y sin theta for theta equal to an infinitesimal epsilon becomes x minus y epsilon, x sin theta becomes x epsilon plus y and z. Of course, all this is correct only up to order epsilon. This has corrections of order epsilon square. Now, all we are saying is that this is the same function as psi but evaluated at slightly different points. Instead of x, y and z, the function has been evaluated at a point which is minus epsilon y away along the x coordinate plus epsilon x away along the y coordinate and at z itself. So we can simply use Taylor series to show that this function, this new function uz epsilon psi at xyz is nothing but the old function psi at xyz. There's a zeroth order term in the Taylor series plus the first order correction. The first order correction will simply be minus epsilon y, the change in x, times the rate at which the function psi changes with x. So minus epsilon y times del psi del x. To that you have to add the change in y epsilon x times the rate at which psi changes with y. So del psi del y. All this of course is correct only up to order epsilon. There is an order epsilon square correction to the whole thing. Now since this works for every wave function, we can just forget about psi in this equation and just write the rest uz epsilon as 1, which multiplies psi here, plus the operator epsilon times x del del y minus epsilon times y del del x, acting on whatever wave function you get. The operator itself is 1 plus first order correction term plus order epsilon square. Notice that this structure should be pretty obvious. If epsilon had been 0, that is, if there had been no rotation at all, the wave function would not have changed. So psi tilde would have been the same as psi, and the operator would have simply been multiplied by 1. So if you are talking of a small angle of rotation, you expect a deviation from the 1, but if you are confining yourself only to a first order deviation, this is exactly what you are going to get. The function changes, but changes because of this particular operator x del del y minus y del del x times of course the angle parameter epsilon acts on psi. Now x del del y minus y del del x should already begin to look familiar. If it doesn't look familiar, just supply an h cross by I and of course multiply by I by h cross to compensate for that. If you do that, it's easy to see that this is nothing but the momentum y component operator. So this is xpy minus ypx, which means that apart from this I epsilon by h cross, this term which generates the corrections or changes due to rotation through an angle epsilon about the z-axis is essentially nothing but the angular momentum component Lz. So on the space of ordinary wave functions, the operator which corresponds to a rotation of coordinates uz epsilon is simply 1 plus I by h cross times the angle epsilon times the operator Lz. This of course again is correct only up to order epsilon. There will be order epsilon square corrections to this. So technically speaking, we say angular momentum operator Lz generates rotations about the z-axis. Now this actually should be pretty familiar to if you have done your advanced classical mechanics properly. In classical mechanics, rotations about the z-axis or infinitesimal rotations about the z-axis are generated by an infinitesimal canonical transformation, and the generator for that transformation just happens to be the angular momentum component. Well, there's nothing special about z. Very similarly, Lx and Ly generate rotations about the x and y axis respectively. Well, there's only one catch here. Not all quantum mechanical systems can be described by a single scalar wave function. There can be more complicated systems. For example, a spin-half particle like the electron is typically described by two component wave functions, one for the spin-up part, the other for the spin-down part. If you are doing the Dirac theory, it's actually described by four different components. And there are other physical systems which can be described by other kinds of objects. We all know that there is a basic linear structure underlying a description of a quantum system. So the objects which describe a state essentially can be represented by vectors in some Hilbert space, vectors which we call kets. But what happens to all this theory that we have figured out for ordinary wave functions when we talk about a general system? Well, it's not all that different. The idea stays the same. All you say is that there is an operator in that particular Hilbert space which changes the vector describing the state in the original coordinate system to a new vector describing the state in the new coordinate system. Now this vector, this operator which changes the vector must have been the identity, if there was no identity of course in that particular vector space, if no rotation had taken place. So if the angle of rotation epsilon is 0, then the operator is just the identity. For a small angle of rotation, there will be a first order correction term, I by h cross times the angle epsilon times an operator, and this operator is exactly what will be called the angular momentum of component along the z-axis, if we are considering rotations about the z-axis for that particular system.